Maybe we will just do this recurrences today. It's better. Let's just do this. So we had a1 equal to 1, a2 equal to 1, and we had this recurrence. And find a. I don't know what happened to others. Yes. So can you find it? So what are A and B, Nandini? I don't know what happened to others. They just don't want to join again. Maybe don't want to join again. Or is there some problem? Let's go to Google. Oh, yes, yes. Okay. So that's why it couldn't join. Ah, I see. Yes, yes. Yeah, I sent the mail. So, but Nandini, tell us, like, yeah, you are here. You should, if you can do it. Let's see. Send them. Right. Okay. So let's just go by the method that we had, right? So the method is just first solve the quadratic. Okay. So what is a quadratic? X square minus x minus 1. Solve the quadratic. So tell me what is x? So we have the same problem. We have the recurrence. We just coming to the quadratic directly, not going into the concept now. Let's come to the quadratic, solve the quadratic. What are the roots? So we know, okay, so does everybody know the formula for the quadratic? I mean, obviously not without the factorization, that is okay, but using the formula?
Oh yeah, minus b plus or minus, right?
Yes, right? So obviously we know it, right? So minus b is just, minus b is 1, plus minus, and so you just do the calculation, it comes out to be this. Nandini, do you know the formula for the quadratic? If not, I will just say it. So that's...
No, sir. I had evaluated.
Sorry, means you do it, so you don't know the formula.
No, sir.
Okay, no, that's okay. So let's just get to the formula of the quadratic. So if the quadratic is this, then what is x? That is the question, right? What is x? Okay. So I mean, how do? We do the middle term factorization, right? Or you can complete the square. That's the other way. So just complete the square, right? When you see the bx, and you want to complete the square, then what will you try to do? Something like this. Right? This looks more closer to sort of looking like going to complete the square. So if this is b by 2, right? If this is b by 2, then you write b by 2 square, right? Minus b by 2 square right? Plus c equal to 0. And now you see, you can just complete the formula, right? This becomes a perfect square, right? And this is whatever this is, minus b square minus 4c by 2, right? And then you can take the square root. So you can remove this. Obviously, there are two possibilities. Both these numbers, when squared, give you x plus b. Give you b square minus 4c by 2. So that's it. There's nothing. Right? It's always with you. So you can always just get it directly. But obviously, once you know, once you get this to topic, you'll practice it enough times, you'll remember it all the time. But this is a form. Okay. I mean, so if someone did not know the derivation, I mean, this is a very good method to complete the squares. So try to complete as many squares. We will do these topics, completing squares, writing things as sum of squares. They're very, very nice topics. But obviously, this is. So now this is the formula, okay? So if you apply this formula.
It's usually A, right?
Yeah, there is a yeah, but since I didn't have the A here, so I didn't write it there also. Yeah,
Okay.
but yeah, you can, if there is an A, you can deal with that. You can divide by whatever. So this is simple. So Nandini, now is it fine? You just apply the formula, right? So the B is 1 and the C is also minus 1, and whatever B is minus 1, C is minus 1. You apply this formula, you get this. Okay. All right. So what does it mean? Now what's next? So Nandini, maybe this is a good time for you to go back and look at the quadratic equations chapter, and maybe just do a few exercises. You just find it in a school text. Do that first, right? The basic school text. Okay. Maybe 1 or 2 grade higher, it will be there. Yeah. So in the week, you can practice it. What do we do next? So we know that one of this is our, I mean, you can call it one of it your A and the other one your B. Right? Then what do we do? And you can indeed check, right, that A plus B is minus 1. Right, I mean, A plus B will not be minus 1. A plus B is 1, right? Because this is, so this is your, now you don't need to do this to solve the quadratic, but just to see that how well it fits, right? That this thing plus this thing is indeed 1. And similarly, you can multiply and you can check that it's minus 1. Okay, that's the product. That's what we wanted. But never mind, we find the A and the B, those are the roots of the quadratic. And they will give you this nice fitting. So now tell me what should be the answer. What is an? Well, as we just did, right? So maybe this x is confusing. So I'll not call this x, I just call this alpha. Right? Alpha. Then, as I just said, right, that the formula is then a to the x times a to the power n, because we don't know what this x is, because the first term and the second term, they don't. So well, let me just go through that. Or basically, as I said, right, the moment you find the, let's just do it directly. The moment you find the roots, you know that your answer is this. So it looks like this, right? But the x and the y you have to find using the first 2 terms. That's what the final thing we came to, right? Just getting there, using the formula without just doing it too much conceptually. Is this what we get? Now find the x and the y. Yeah. So how do you find the x and the y? That should be simple. So to find the x and y,
just plug in values for A1 and A2, right? You
exactly.
form 2 equations.
Right. So A1 is 1, and so what is the equation we get? What's the first equation?
So and then x times 1 plus root 5 over 2 to the power of 1, right? And same for y.
Yes. So it's a little there are irrational numbers and so on, but that's okay. We shouldn't be afraid of it, right? That's like that. We cannot help. Okay. So and then similarly y similarly
It'll be the
A2,
same thing, yeah.
right? But what will do the equation?
1 plus root 5 over 2 squared, yeah.
Yeah, so what is it? So something you can say 6, I don't know what it is, 6 by this by 4, 3 plus root 5 by 2, right? 5, 3, so I'll suppose it's 3 minus root 5 by 2, right? Conjugate of square of the conjugate. So square of the conjugate is conjugate of the square, right? We had the square, take the conjugate. So anyways, you can just calculate it, and that's it. This is, and you find the x and the y. Do you want, anyone wants to find the x and the y? Well, you have to find it, whether you want it or not, right? You have to do this problem, you should find it. So let's find x and y. Tell me what. You could also try to guess, hey, if you want to guess. Yeah, it's a little clumsy, but you have to solve it. So solve for the x and the y, and then tell me what comes out. So we are basically able to solve all equations like this, and that's at least that's what we see, right? And that's a very good thing. But let's find this exactly. Then we can do some checking also after this. So there are two things that you guys have to practice this week. If you are not comfortable with these things, there are two things which you have to practice, the basic things. And number one is, and you should note it down, you should do it, because these are the basic school topics, which I don't like. I don't do the practice part, right, too much, at least for the basic topics, because we cannot do all this, everything. But you can do it on your own and just, school, or ask some parents or some friend, whatever. Just look at, see, in the book, the rules are there. Just ask me if there is anything conceptual. This simultaneous equations, okay, linear simultaneous equations, one, and quadratic equations. Even if you know the formula, you should practice it. If you're not, and if you know, then if you practice, then practice a harder problem, the miscellaneous and so on. There are more interesting questions. But these two things you just practice. So keep 2 days for simultaneous equations and 2 days for this, and just practice and get good at it. Because now you have a real reason to do it. We came from the sequences thing to here, right? And now we need to solve simultaneous equations and quadratics. Like if you were really good at those two things, then this topic you could have just done it yourself. I would have just told you the first hints, right? So that's the level of, I'm basically combining the insights from quadratics and that to present this topic in this way. That's all, nothing more. So what is x and y? Okay, maybe I'm just disturbing, saying too much. Find x and y. Right? So cannot solve it, just solve this, right? So just multiply, make the coefficient of x same, right? So you write this, make the coefficient of x same. So you get x times 3 plus root 5 by 2. Because if you solve it now, then you can check some things that is actually correct and so on, right? You can appreciate the fact that this formula is actually giving us the next terms correctly. That's why I just wanted to see if you can solve this. And solve it now. And we get this. And then you get this. It's a little clumsy, but it's okay, right? do it. And then this also is same. That's why we are doing this. So we don't need to check that. And then there is 3 minus root 5 times. So I'm multiplying the second equation by 1 plus root 5 by 2, right? And then we subtract this two, right? So when you subtract this, what do you get? Subtract the left hand sides, what do you get? 3 by 2 minus 1 by 2. Come on, tell something. I just
One.
right, it's 1. And then what is y? Do you simplify and see what y comes out? That I'm really fine. That's it. This is the last thing we have to do. Just solve this. So we get 2, 3 root 5. No, so there is, so that 4 is there. That y by 4. Five, 8 plus 2 root 5. 8 plus 2 root 5, right? So the 4 will become 2. 4 plus root 5. Okay. And so you see the y comes out to be a little clumsy number, because maybe I should have taken this to be 2. Then it comes out to be a slightly better number, but it still has square roots. I mean, these will always be there. X and the y may get a little simplified, but either ways. So the y comes out to be 2 by 4 plus root 5. And correct. And then check what is the x. Find the x. For this, you can just put in one of the equations and do. Okay. Okay. So then do this for homework. Fine. Right. And then basically after that, but the point is you don't want to cube that and check that actually is 2. Okay. But it does turn out to be. Right? You can. But you can. So we have learned how to solve this thing. So we know that this thing. So we know that an will look like. So well, the standard formula, sort of I remember, it comes out like this: 1 plus root 5 by 2 to the n plus minus. And we'll just check it. By 2 to the n. So we did not get this, but there's a reason. So when you put n equal to 1, then what do we get? So we get 1, right? In this formula, let's check. When you put n equal to 1, you get 1. Okay. Put n equal to 2 and check. So the point is you start with 1 and 2, then you get this formula. Okay, I started with 1, so I got a more complicated. So just put n equal to 2. Only the term with the square root will remain, right? So you will have a square plus b square plus 2ab. Oh. And yeah, and then you get 2 times this. You calculate this, you get 2 times this. After taking the difference and so on, right? And then you divide this by this. You just put 2 here and check what it comes. And you will get 2.
1.
Right? So finally you will get 2. It's 1, and then this is also minus 1. So the point is that if you start with 1 and 2, then you get this one. Okay. Otherwise, you'll get more complicated. You get the solves. So the point is that this Fibonacci, now would you call this a formula? That's up to you. It's not helpful for a lot of things. It's helpful for a lot of things. So, and those maybe we'll see from time to time.
A2 should be 1, right?
A2, no, this is 2. Okay. It's not 1. There are 2 terms, right? It is 2 times root 5 by 2. It's 2 times that, right? Yeah. Just check it. It does come.
Yeah, by 4, right? By 4.
No. It's not by 4. No, it's not by 4. It's 2 AB. You check it. It comes. I mean, yeah, you check it. It will come out. It's A plus B whole square minus A minus B whole square is 4AB, right? So yeah.
Yeah, and you square the denominator also, right?
No, but still it's 4AB. So
Okay.
Is it?
It should be 1.
Okay, right. Oh, okay. So then maybe something in the calculations, right? No, sorry, yeah, because there are both are half.
No, this is correct, right? First 2 terms should be 1 and 1.
Yes, yeah. So if you take first 2 terms as 1 and 1, then this comes out to be the formula, right? You're right. So basically, the y we found was some calculation mistake somewhere. Okay. So otherwise, so basically, the x comes out to be 1 by root 2, and the y comes out to be minus 1 by root 2. Yeah. If you do the calculation, this is what you will get. Okay. And then you get this formula. Right. No, you're right. Sorry. Yeah. Okay. That's a small point. But you should solve this and check it for yourself that you do get this. Don't make the mistake like me. Okay. So that's right. Now this is useful for a lot of things and so on, but we will see that from time to time. But we have learned to solve the problem. Now you see this is something fundamental going on here. To understand this sequence as a formula explicitly, we have to go outside the realm of rational numbers. Okay. So you see, this is what the thing is, right? So you have a very complicated sequence, right? I mean, the Fibonacci sequence is complicated, more complicated than the geometry progression and the arithmetic progression. It's a difference of 2 geometry progression. Okay. In that way. But the point is that this complicated thing, so you've increased the complexity, okay, of the sequence. But if you still want to talk about it in a simple way, then you have to increase so that complicatedness of the sequence, yeah, that we put in the number system, and we get a simple language to talk about it. Okay. So if you're willing to make the number system complicated, and that kind of swallows the complexity of the question and gives you a simple form. Okay, so you have that bargain is always there. There's really never any true gain in a way. Okay, something is complicated, it is complicated. Okay, but we are used to these irrational numbers and we can handle them, rationalize and so on and so right. So if you're willing to call this number like a simple, if you're willing to call this alpha and this an alpha 2, you're willing to put that, then you get very simple formula. So this is also a formula which is simple in a way, if you're willing to call those numbers simple. So you expand your number system and then you get a formula. Similarly, for something else, you have to expand the number system further and get that. So but what we want is that we want to convert that complexity, which is maybe combinatorial or which may be coming from some words. We want to put that complexity systematically in a number system. Okay, so that we can deal with it in a systematic way. Put that complexity in a organized manner, and then we can deal with it. This is what maths, a lot of it is. Okay, so you have a function, then you make a matrix out of it. Now, is that simple? Well, it depends. So, but basically, we get an analogy, right? Analogy is that now it becomes a sum of 2 geometry, because you're willing to call root 5 a number, and hence 1 plus root 5 by 2 a number. If you start to call that, it's a non-trivial thing, right? It's not a number in class 2 and 3. It's maybe suddenly it becomes a number in some grade, right? Root 5 suddenly starts becoming a number. But if you're willing to start calling that a number, then you can use your old language of geometry progressions and say that this is the sum of geometry progressions. Otherwise, the Fibonacci sequence, you would have never heard it, it's a sum of geometry progressions. You would see that it's just sum of previous two terms. And that's a very easy rule, I don't know, whatever, but it's not easy enough to help you to find the 100th term without going through the process, right? But if you're willing to expand your number system, then you can use the old simple language to talk about these new things and hence gain insight into the sequence. How you gain insight into the sequence? Well, for that, one has to see some applications of this. You see what's happening, right? This is a very interesting thing that happens in maths. Okay, expand your system, and then the old thing, you can talk about the new thing in terms of the old thing, and then it's in a comfortable position, right? When you're able to talk about something in an old language and some familiar language, like, oh, this is just a power of something, and then you gain new insights. Okay, so we will see the insights. You'll see applications of this formula maybe sometime later. Yeah, and by the way, this is called the Binet's formula. This is a name that doesn't really matter. The Binet's formula. Okay. Right. And this number is obviously, you may know, this is a very special number. This is the golden ratio. Somehow all the good things start happening at one place. It's called the golden ratio. Okay. And well, if anything, one thing which you can learn from here is, you see how this leads to insights is like this. When n becomes very, very big, so okay, can you check that this number is sort of between 0 and -1? Do you agree with that? Right? I mean, root 5 is what? -2 point, root 5 is what? 2 point something, right? And 1 minus that is 1 point something, divided by 2, it is 0 point, -0 point something, right? It's between 0 and 1. So when you raise it to higher and higher powers, it sort of loses its value. This becomes almost nothing. Okay. So when you increase the value of n, this just vanishes. Sort of, it becomes negligible as you want it. Okay. And then this your sequence basically just is this. I know up to any practical approximation, it is this. It can be made more than, in the sense that, but anyways, leave that. Point is, it's mostly just this. Okay. And that's the insight that you would not gain from if you don't introduce root 5 as a number, or you don't solve this recurrence. Okay. So then you know that the Fibonacci sequence is just this. And then you know that if an is the nth term and an -1 is this, then basically this is, take the ratio, right? What will the ratio be? Well, it will just be this, right? Because you put n and then you put n, because you're forgetting this sort of up to approximation, more or less, it's just not there, more or less. It's 0.00000, and then you go to make n and you go to 100. Okay. Check the ratio, it is just this. Then it's almost a geometry progression, almost geometry progression. And the ratio is almost this, not equal, it's almost this. That is very simple, right? Then things start becoming very simple. Then you take log of it, it becomes arithmetic progression, right? And so on and so on. Okay, so this is one of the, but there are many implications of this part. So maybe we'll stop here. Okay? I'll just maybe give a small exercise, which is not related to this, if you would maybe see in one sense, but try this, it's a good problem. Okay? It's related, but I don't know, so you have to check. So, so what is the question that is has to ask? Maybe I'll start, let's see, I'll try to make it up. So, and so I'm starting with a rectangle. Okay. And now, okay, so let's say I start with some rectangle. Okay. And then I make a square in it. You may or may not have seen this construction. You make a square in it. Okay. So you have a rectangle and then you make a square in it. Okay. And so when you make the square, right, you get this other rectangle. You get this other smaller rectangle. This is a rectangle. This is your R2. And your bigger one is R1. Okay, bigger rectangle is R1. So that R1 is similar to R2. I'll define what similar mean, but you can sort of understand in a vague way. Similar means that, so you the big rectangle, right? And you look at the small rectangle. A big rectangle is similar to small rectangle means that you can sort of, maybe you have to take the rectangle like this, big rectangle, and turn it like this, right? And then shrink it means zoom it in, in the same ratio for both height and base, right? So that it becomes a smaller rectangle. That's what I mean. I'll still make it more precise, but just to give you the intuition. Okay, so you fit in a square, you take away the square, okay, and you get the smaller rectangle to be similar. That doesn't always happen, right? So then, if this is the situation, then this situation, let me, as I said, let me make it precise. To make it precise, what I mean is that this is A, right, and this is B, right, and this is B, and let's say that this is C. Now I'll leave you to do the calculations. This is C, right? Then all I want to say is that A by B, that is a ratio of the bigger side to the smaller side of the first rectangle, is the same as the ratio of the bigger side to the smaller side of the second rectangle, which is, by the looks of it, looks like B by C. Okay, that's what I mean by similarity, right? The ratio of the sides is same, the natural notion of similarity. Given this, find A by B. I mean, so those kind of rectangles are picture perfect. You would have seen, right? Those are for certain reasons. I mean, I could get into that between the midpoints and join and sort of converges, and so it looks good and so on. But but just do this problem and find A by B, find the ratio. Okay. So this is one question. I'll just use I mean, you can just take some, you cannot take numbers here because, I mean, you have to find the number. So you have to see what A by B comes out to be. But the C you can calculate in these sum terms. That's a square. That red one is a square. Don't forget that. That's a square. Okay. It doesn't look like a square because my picture is not picture perfect. I have not gotten the correct ratio, but it's a square by stipulation. Okay, so you have to, all right, that's a square. The next question, which surprisingly all the three questions, one question we solved today and this question and the next question might be connected. So you have to check. Okay. So the next question would be like this. And 1 minute. So, okay. Yeah. Find lambda. It came from a logarithm question, but I don't remember that exactly. I don't want to try to remember all that. But just the crisp question is, wonderful question is this. Find lambda where this is. So there was another number here and there was another number here. Yeah. And what were those two numbers? They were like this. Okay, I find it. Try to guess it, what you wanted to do. There's an analog of this. It comes later, which we'll talk about, but try to find 9, 12, and 16.
Sir, what is lambda? Is that just like a variable?
Yes. Yeah. Find a lambda such that 9 raised to the lambda plus 12 raised to the lambda equals 16 raised to the lambda. Okay. Now see, these may not be trivial. You may not be, but just try it. Try it. Just see what you can see if you can say something about lambda. 3 problems, you will see surprisingly similarity in this thing. Okay. So this is sort of, I got asked this today by someone in the library, just someone preparing for some exam. The first one is sort of a classical, which I read somewhere, and today sort of, and then just combine them. These are, you'll see they are very, very similar. There is the answer to them will be the same. Okay. Yeah. Okay. So let's try it. So note it down.
What is the third problem again?
Yes, you have to find the lambda. Find the lambda which satisfies this. Okay.
Okay. And the second problem is find A by B.
Find A by B. Right, find A by B. So you start with, so there is some rectangle which one side is A and second side is B. And it's a very special rectangle because when you cut out a square from the corner, then this rectangle is similar to it. And I've written that precisely what that means. Means bigger side by smaller side of the bigger rectangle is same ratio as bigger side by smaller side of the small rectangle. I've written that. Now use that to find A by B. Okay. And earlier A by B was coming out to be 1 plus root 2 by 1 plus root 5 by 2. The earlier problem, the Fibonacci sequence, and these two here. Okay. All right.
What is the first problem?
No, so that we sort of already did. So the Fibonacci sequence, right? The ratio was coming out to be roughly 1 plus root 5 by 2.
Okay.
Right. And is this also the, I don't know. I don't want to say that. You have to find out and check. Okay. Right. Yeah. Okay. So note it down and then after that you can leave. Okay. And if there is any question, then please ask now. Don't, if you, yeah, especially if the question is not clear and to anyone, just, Nandini, are the questions clear? Ask if there is anything. See, this are very random questions. Okay. These are not typical questions, but just understood it. That's the main thing. Okay. All right. Otherwise, then you can leave. I'll also leave. Just note it down. Okay. All right.
Yeah, thank you, sir. Bye.
Thank you, sir. Bye.
Wait, are you saying? Oh.
Shubham, that equation, right? A by B equal to B by C. That's a geometric mean, right?